the Comptia Network Plus course, protocol analyzers, also called sniffers or network monitors, are used to capture packets in their raw format as they cross the network. Windows desktop operating systems before Windows Vista came with a built-in protocol analyzer called Network Monitor, but that is no longer the case, although you can download one for free that will work with the newer operating systems. The Network Monitor tool that comes with these operating systems will capture only packets that are sourced from or destined to the computer on which the tool is running. Commercial sniffers like Wireshark and OmniPeak can capture any packets because they set the NIC to operate in promiscuous mode, which means the NIC processes all packets that it sees. Protocol analyzers can be used to determine the type of traffic that you have in your network, and depending on the product and the bells and whistles contained therein, you may be able to sort the results based on port numbers, protocols, and so on. Another use of a sniffer is to examine the traffic that should be occurring on the network when something is not working to aid in troubleshooting. These devices can capture and display all packets involved in the connection setup, including, for example, request and respond headers to a web server. For example, earlier in the book we discussed the operation of DHCP, and you learned that there are a series of 4 packet types that must occur for a DHCP client to receive an IP configuration from a server. As a review, these packets are as follows: DHCP discover, DHCP offer, DHCP request, DHCP acknowledge. If you turned on the analyzer and then executed the IP config release and IP config renew commands on the client, more on these commands later in this chapter, you should see these 4 packets in the analyzer capture file. The packets would be intercepted with the hundreds or perhaps thousands of other types that will be captured. By using the display filtering options in the software, you can easily segregate out the DHCP traffic. An example of DHC process can be seen in a capture as shown in figure 17.1. So you can see here's figure 17.1, and we see here DHCP discover, DHCP offer, DHCP request, and DHACK, which is acknowledge. If all you saw in the capture were the DHCP discover packets with no DHCP offer packets, you could reasonably assert that the DHCP server is not receiving the DHCP discover packets. Perhaps it is located in another broadcast domain, or perhaps it is not on. Additionally, you could examine fields in the DHCP offer packets that may tell you that the DHCP server is out of addresses. The point is that the tool can be used to troubleshoot issues, but try to troubleshoot the issue. Throughput testers. Users on a network often complain about the speed of the network speed is in some ways a personal perception, because some people have more patience than others. To determine when a network slowdown is real as opposed to perceived, you need to actually measure the throughput. That's what throughput testers are used for. These devices, typically software based, work much like a protocol analyzer in that they measure the traffic seen on the network and can also classify the type of traffic that is eating up your bandwidth. Is probably what you already know. Figure 17.2 shows one version of the software by Tamosoft. The software is installed on a server and also on the client. In the figure, the software is measuring traffic between the client and the server. It shows the throughput for traffic in real time and is in the shot is breaking the the traffic up by unicast TCP and broadcast UDP types and in bidirection. Earlier I discussed the importance of baselines, that this is another area where they are important. Network throughput figures mean little without a baseline in which comparisons can be made. How do you know what is abnormal when you don't know what is normal? Baselines should be taken when a network is operating well, but they should also be taken when when traffic load is normal. Connectivity software. There are many times when you need to make a remote connection to a machine to perform troubleshooting, but you are miles away. Connectivity software is designed to allow you to make a connection to the machine, see the desktop and perform any action you could perform as if you were sitting in front of it. Microsoft has made what it calls remote desktop software available for free. Windows products since Windows NT. When this software is installed by default in later versions on both source and destination computers, a remote desktop connection can be made. Commercial tools are also available that of course claim to have more functionality, and they probably have a few extra bells and whistles. These include logmein.com and GoToMyPC and others. Figure 17.3 shows a session window for a logmein.com session. The advantages of these connectivity tools are obvious. With these tools you can do anything you need on the machine as long as you can connect. They also allow you to see what the user is actually doing when they encounter a problem, rather than having to rely on what they tell you they are doing. You can even show a user what they are doing wrong. Most of these tools allow for chat sessions and for either end of the connection to take control of the machine. You can also transfer files to them if required. Maybe a DLL got deleted, for example. Using Traceroute. For starters, let's pose these questions. Where do all these packets really go when we send them over the internet? And how do all the packets actually get to their destination? Well, we can use the TCP IP Traceroute in Windows command line utility to help us answer both questions, because its output will show us every router interface a TCP IP packets pass through on the way to its destination. Traceroute, trace for short, displays the path a packet takes to get to a remote device in all its glory by using something we call IP packet time to live, TTL, timeouts, and Internet Control Message Protocol, ICMP, error messages. Also, it's a handy tool for troubleshooting an inter-network because we can use it to figure out which router along a path through the internetwork happens to be causing a network failure when a certain destination machine or network is or suddenly becomes unreachable. To use Traceroute at a Windows command prompt, type Traceroute space and the domain name service. DNS name or IP address of the host machine to which you want to find the route. The Traceroute utility will respond with a list of all DNS names and IP addresses of the routers that the packet is passing through on its way. Plus, Traceroute uses TTL to indicate the time it takes for each attempt. Following is the Traceroute output from my workstation in Boulder, Colorado to my lamel.com server in Dallas, Texas. So you can see here's the output there in command prompt. Trace complete. Were you able to see the packets bounce? Were you able to see that the packets bounce through several routers before arriving at its destination? Good. This utility is useful if you are having problems reaching a web server on the internet and you want to know if a wide area network WAN link is down or if the server just isn't responding. What this means to you is that basically wherever the Traceroute stops is a great place to start troubleshooting. No worries here, though the previous outputs show that every router is up and responding. Last notice in the output.ms. This is the latency of each hop, meaning the delay. Traceroute or Traceroute is a great troubleshooting tool you can use to find out where your network bottlenecks are. If you use Traceroute or Traceroute and receive an asterisk, this indicates that an attempt to reach the router took longer than the default timeout value. This is very good to know because it can mean that either the router is extremely busy or a particular link is slow. Another reason for getting an asterisk could be that the administrator has disabled IMCP on the router and that the packet is trying to hop through. Why would someone want to do this? For security reasons, that's why. It happens to be a typical strategic move done on routers that interface to the ISP to conceal their actual location so bad guys can't hack into them and therefore your inter-network. So I'm going to leave it here today for this video. If you like listening, please consider like, share, subscribing and giving a thumbs up. Thank you.